Hello, multivariable calculus students. This is Mr. Johnson, and this is section 11.3, which is on partial derivatives. So the first part of your notes has many of the definitions for partial derivatives and the notation. So here is the limit definition of a partial derivative, and I'll explain how to calculate the partial derivative in just a moment. It's actually a really easy process, but it is certainly different than what you've experienced in the past. You sort of have to keep track of your variables and what type of partial derivative you have. So this first limit definition is the partial derivative in terms of x, and the second one is the partial derivative in terms of y. So this would be, for example, a function of xy. You can write that as f of xy, for example, equals z. You may have a different rendition of that, but if we're talking about space here, we have the variables x, y, and z, and so this is sort of our standard. And again, you can see that it's very similar to what we have in single variable calculus, where we let x vary by a value h, or for the partial derivative of y, we let y vary by a value h, and we let that value of h go to 0. And so what we're doing is taking essentially the slope of a secant line. That would be this difference quotient right here. So the slope of a secant line from one point to another, and we let that point get infinitely close, which is where the limit comes in, and it becomes then the slope of the tangent line. So what we're looking at here in general, and I'll show you a couple visuals, is the partial derivative as the slope of a tangent line in a particular direction. So we're looking at the partial derivative with respect to x and the partial derivative with respect to y. There's many notations for this. The primary ones that we're going to use would be certainly the partial derivative based on f of x. We also have the differential form, and notice that the d that we're used to writing definitely looks different now. So the differential form, Leibniz form, looks a little bit different. The other ones I don't use quite as much, or I haven't seen quite as much in different textbooks or in different curriculum. However, depending on what the function's name is, you may see in terms of z rather than in terms of f. But again, these are just a number of different notations that you have to be aware of. All right, here's the rules for finding the partial derivatives, and it's actually really, really simple. So if you're trying to find the partial derivative with respect to x, you regard y as a constant. So in other words, you just pretend like y is the number 4 or something like that. You just treat it as a constant through the whole problem, and you differentiate with respect to x. For y, of course, it's the exact opposite. So x is the constant, and you differentiate with respect to y. Below are derivative limit definitions of a derivative at a point a, b. And what I'm going to do here in example 1 is I'm just going to show you how to take these partial derivatives. And again, it's very straightforward. You just have to practice a little bit, and you will get the hang of it pretty quickly. So we're going to first calculate the partial derivative with respect to x. And we're going to treat y as a constant. So we have the derivative of 3x cubed, which would be 3x squared. Obviously, that has no difference to what we are used to in single variable calculus. Now, when we look at the derivative of x squared y cubed, keep in mind that y cubed is just a number. So it sort of just tags along as you take the derivative of x. So we have 2x y cubed. Again, y cubed is that constant. That would just continue. This is not the product rule, keep in mind, because y is considered a constant, not a separate function. The derivative of minus 2y squared would be 0 because y is a constant. So that's it. That's the partial derivative with respect to x. And if we're trying to figure this out at 2, 1, we would simply substitute in 2 for x and 1 for y. And so what we get for this one is going to be 12. So that would be the partial derivative with respect to x of the function f at the point 2, 1. So if we were to locate that on the surface, and again, I'll show you some visuals of a different problem in a little bit. So if you were to locate that point on a surface and you were to take a look at the slope with respect to x, your slope is going to be 12. Now let's take a look at the partial derivative with respect to y. So now we're treating x as a constant. So when we look at x cubed, that derivative is going to be 0 because the derivative of a constant is 0. The next portion, x squared, is the constant, and so we have the derivative, which would be 3 x squared y squared, and the derivative of minus 2y squared will be minus 4y to the first. And then we're going to take a look at this partial derivative at the point 2, 1 as well. So we substitute in 2 for x and 1 for y, and this time we get 8. Okay, let's look at a couple more examples on the next page. All right, here is the interpretations of the partial derivatives as the slopes of tangents. So I will try to explain this in more detail in the next example, and I have some diagrams to follow, some graphs that might help you visualize this. What I'm also going to do is I'm going to include an additional video resource in our notes here after this particular lesson video, and that will just give you a nice visual as to what the partial derivative is. But here's what happens. So we take a surface, and when we take, for example, the partial derivative with respect to x, we're going to let y be a constant. Now, when y is a constant along a surface, you're going to get a curve. So for example, if you notice you have C1, which, let me put it in a different color, let's do green. So you have C1, which is a curve along the surface, and notice that if you were to let y be a constant, let's say y was 3, along this green curve, y is always 3. That never changes. In fact, and you'll see this in the next problem, if you were to let y equal 3 be a surface, it would be a plane. That plane would slice through this blue surface, and it would be a plane that is parallel to the xz plane. And as you slice the surface, the blue surface, by y equals 3, you would get this C1 curve that, again, would just be a space curve along the surface. Now what we're doing is we're taking that particular curve and we're looking at a point on that curve on that surface, and the partial derivative would be the slope of the tangent line associated with that particular curve, and again assuming that y is a constant and x varies. Now the same thing is going to happen, but really in the opposite manner when we look at a partial derivative with respect to y. So we're looking at the curve C2 that goes along this particular surface. That would allow x to be a constant. Let's say that x is equal to 2. So x equal to 2 would slice a plane through this surface, causing this curve in space on the surface, which is C2. And again, you're going to look at a point on that curve, and if you were to look at the slope on that particular curve in space, then that slope would be the value of the partial derivative with respect to y, and that would be when x is held constant. So what we're doing with partial derivatives is we're sort of taking this idea in space and we're simplifying it down to single variable calculus in a lot of ways. We're just simply taking a look at a curve that is in space, but the curve is associated with one particular plane, which means that we kind of are reverting to just a plane in space, and we're analyzing the curve and the tangent line associated with that curve. So that's what we're doing with these partial derivatives. Okay, let's look at the next problem and see if we can make a little bit more sense of this. So with this problem, we're going to look at the partial derivative with respect to x, which is simply negative 2x. Remember, the derivative of 4 is 0, and the derivative of minus 2y squared is 0 because y is, could be considered a constant. The partial derivative at the point 1, 1 is going to be simply just negative 2. And then we have the partial derivative with respect to y, which is negative 4y at the first, and we evaluate that at 1, 1, and we get negative 4. Okay, I'm going to try to help make some sense of what's going on with this particular one. So I'm going to dig into what we've done in the past couple sections and try to make some connections, okay? First off, let's take a look at, and I'm going to refer first to our partial derivative with respect to x. We are evaluating that partial derivative at 1, 1, and we got negative 2. So if we were to look at our surface, and the surface is going to be obviously this blue set right here, and this is just shown in the first octant. But anyway, this is the surface here. Here's the point 1, 1, and obviously if you were to look back on the original equation, if you were to substitute in 1, 1 to the original surface, you would get a z value of 1. So the point we're analyzing is 1, 1, 1, and the plane, you can see this, it's a slightly lighter blue color. The plane will exist when y is 1, because remember, with the partial derivative with respect to x, and we're evaluating this at 1, 1, we got -2. The partial derivative with respect to x is assuming that y is a constant, and because we're dealing with the point 1, 1, 1, that means that y is equal to 1, which again would cause us to get a plane in space. Now again, this diagram is simplifying the amount that we see of the plane. So this particular plane would obviously continue forever. We're just seeing the portion of it that intersects with the surface. When it intersects with the surface, so you intersect the surface and the plane, you end up getting this curve right here, which they're calling C1. And that curve is what we're trying to analyze. And we're trying to figure out what the slope of the tangent line is when it intersects that curve at our point 1, 1, 1. And that slope happens to be -2. And you can see that in the diagram that makes some sense, at least, that it has a negative slope. We can sort of try to put ourselves in that picture for a moment and take a look at the slope and how it changes. And that slope looks to be -2. If you were to move over and look at the second portion, you can really see a little bit more clearly the surface itself and how the plane cuts into that surface. And again, here's that curve C2 that formed right there. That's that intersection between the plane and the surface. And then here, everything is stripped away, and we are looking simply at the curve, and we're looking at the tangent line. And so that's what we're doing with these partial derivatives. Okay, you can take a look at the diagrams below, which show just the partial derivative with respect to y, and it's really a similar approach. And I think it's helpful to see what we're trying to accomplish with these partial derivatives. Okay, I want to make one more connection to our previous units, and that is that I want to think about this in terms of vectors really quickly. So if you were to take a look at this particular equation, which is z equals 4 minus x squared minus 2y squared, and if we were to think about this as a vector function, a surface related to a vector function, we could write this as r of, let's just make it u and v to connect us back to chapter 10 for just a moment. Let's say that we want to let x be u and we want to let y be v. Well, then z would simply be 4 minus u squared minus 2v squared. And this was section 10.5, if you wanted to make a note of that. And in 10.5, we talked about how we can represent these surfaces as vector functions of two variables. So in this case, all I'm doing is letting x and y be the variables u and v, and then z is made up of them in this particular extent. If we were to think about this, kind of to backtrack a little bit in our study in chapter 10, remember in chapter 10 we also talked about curves in space, and curves in space had a vector function of one variable. Now I know that the surface right here has the variables u and v, but remember when we're thinking about the partial derivative with respect to x, we're going to let y be a constant. So when I think about just the element of x changing where y is a constant, I could kind of think about a vector function related to the curve that exists in the diagram below. So I'm thinking mostly about that curve 1 that we were discussing in this picture down here, where we're looking at this change of variables, but really y is just always 1. X is the only thing changing. So let's say that we were to look at that curve C1, and I'm going to call it R of t because that's what we did in chapter 10 a lot. Well, really what we're dealing with then is this change in x, which we're going to call t. I'm just going to let y be itself just for a moment, and I'm going to represent z in terms of t and y. Now, they're going to be the same thing here. The reason that I'm only calling this vector a change of one variable is simply because we're letting y be a constant in this moment, more or less. So this is not going to produce, this red equation will not produce a surface. This red equation will produce a curve. Specifically, it's going to represent C1, the one that we're analyzing right now. Now, if we were to take the derivative like we did in chapter 10, we would have 1, the derivative of y is of course 0 because y is a constant in this example, and we would have -2 times t, and of course the derivatives of y is going to be 1. Now remember, we're dealing with x equal to 1 for our particular point, because we're dealing with a point 1, 1, 1. So if t is the representative of x in this example, this connection to chapter 10, that means that t is 1, and we have the vector 1, 0, and negative 2. And remember, when we calculate r prime, when we're talking about a curve in space, we're talking about the slope. And then we wrote equations for tangent lines, for example. We found the unit tangent vector, for example, when we studied section 10.4. And if you notice, this is actually the slope, and this is directly connected to the partial derivative that we got originally, that slope of negative 2. Notice how the vector 1, 0, negative 2 will in fact be the identical slope negative 2, but in vector form. So there's a deep connection between what we did in chapter 10 and what we're now doing in chapter 11. Keep in mind that the form of what we're doing is completely different now, because chapter 10 was all about the vector representations of surfaces and curves and slopes, and now we're working into that Cartesian form of surfaces and slopes and so on. So the partial derivative feels like a new concept, certainly, but it is directly connected to how we studied change in chapter 10 in vector form. Okay, let's move on to the next page. All right, we're just going to do another example for number 3 here. This is nothing really new, except that it's a different surface, but the derivatives that we're doing, same process. Notice that the notation for this one does change, so we're using this differential notation, which I know looks a little bit goofy. The derivative of sine is cosine. We keep the inside. Now we're multiplying by the derivative of the inside, but keep in mind that it's with respect to x, which means y is the constant. And that means that all we have here is the derivative of the inside, which is just 1 over 1 plus y. Remember, y is the constant, so that's kind of like the coefficient of x. And then that will be your derivative. So that's it. That's the partial derivative with respect to x. You have then the partial derivative with respect to y. And this time, of course, we have the same initial setup because the derivative of sine. Keep the inside, but now what we have to do is take the derivative of the inside with respect to y. One way you might want to think about this is that you have x times 1 plus y to the negative first, and remember x is the constant, and so the derivative of this would be simply negative x times the quantity 1 plus y to the negative second, and that's just the power rule. So again, if we were to take the derivative with respect to x, we would get just the power rule of differentiation. And we could write that, if we'd like, as negative x divided by the quantity 1 plus y to the second power. And those are your two partial derivatives. Okay, let's tackle one extension to this. And we're going to talk about a number of extensions to these partial derivatives, but if you remember back to single variable calculus, and maybe I'll just give you a really quick example here. Okay, so if you had, for example, x squared plus xy equal to 4, and let's say that we wanted to find the derivative of y with respect to x. So this would be, a really common style question for both A, B, and BC or BC calculus. When we were to take the derivative of this with respect to x, y is implicit. However, you're stuck with this situation where, the x's and y's are on one side of the equation. We could certainly solve for y and handle it that way, but I'm just giving you a really easy example to show implicit differentiation. So we would take the derivative of x, and then we would take the derivative of xy. Now, we're not doing partial derivatives here because we're in the world of single variable calculus, and we never knew what that was then. So we're doing a product rule. We're doing the derivative of x, which is 1 times y, plus the derivative of, x times the derivative of y, which is dy dx, and the derivative of 4 is 0. And we're trying to solve for dy dx, and so we're going to move things over to the right side of the equation. So we have negative x minus y, and then we would just simply divide by x. And we would get our slope as an implicit equation and finding the derivative of that. What we're going to do with partial derivatives is really similar to that. So if you notice in this particular problem, we have this really ugly equation, and we're going to try to find the derivative of z with respect to x and the partial derivative of z with respect to y. I'm going to rewrite the equation below just because I used up a little bit of space here. So we have x cubed plus y cubed plus z cubed plus 6xyz all equal to 1. So notice that the x's and the y's and the z's are all sort of stuck on the one side of the equation. Also notice that if we were to try to solve for z, we would have a problem doing that. And so it's not written in the form that we have used so far in our examples. So for example, if you go to example 3, we have f of xy equals, you could write that as z equals if you wanted to, and that is not the same type of form that we're in with example 4. And so it's a little bit more difficult now because the z's are sort of stuck more or less with what we're doing with the other variables, and so we're going to do an implicit partial derivative. And again, it connects directly to what we do in single variable calculus when we do implicit differentiation. So we're going to try the partial derivative with respect to x first. So keep in mind that y is a constant and z is implicit and x is just the variable of differentiation. So we have the derivative of x cubed, which is of course 3x squared, the derivative of y cubed, which is 0, plus the derivative of z to the third, which is 3z squared. However, z is implicit, and so we get the implicit derivative operator, plus, now 6xyz is a product because you could think of it if you wanted to as like the derivative, the product of, let's say, 6xy times z. So it's the product between two functions, one non-implicit, the other one implicit. So we have, let's see, the derivative of 6xy, we can make that just 6y and then multiply by z plus 6xy, and then the derivative of z is the implicit differentiation of that, and then the derivative of 1 is 0. Now our goal here is that we're trying to solve for dz dx, the implicit derivative of that, partial derivative of that. So we're going to keep all of those items together on the left side. And then let's go ahead and move the other items over to the right side by subtraction. Okay, I'm going to factor out the dz dx. So I have 3z squared plus 6xy. I have everything on the right side that sort of stays the same. And then our last step here would be to divide in order to solve for our implicit partial derivative. So we have negative 3x squared minus 6yz divided by 3z squared plus 6xy. We could, I suppose, simplify that a little bit, but that's okay with me just to leave it for now. There's your implicit partial derivative. Okay, now we're going to do the other one. So that is going to be the one in terms of x. So now what we're going to do is take the same thing, but we're going to do this in terms of y. So here's our starting point. And again, we're going to take the derivative with respect to y, and that means that x is the constant and z is implicit. So we have the derivative of x cubed, which is 0, derivative of y cubed, which is 3y squared, plus 3z squared times the derivative of z with respect to y now. We have the same type of product rule, but again, y is our variable change, not x, so x is constant. Excuse me, so we have 6 xz plus 6xy times the derivative of z with respect to y, and it's all equal to 0. Okay, same strategy here. We're trying to figure out we're trying to solve for dz dy. So we're going to group those together. Okay, so then we'll factor out the dz dy, and then we'll leave everything on the right side. And our last step would be to solve for dz dy. And again, we could simplify that, but let's go ahead and just leave that partial derivative of z with respect to y. Okay, that's it for this video. In the next video, you will see some higher order derivatives. Thank you.